Welcome to qnawire.
Here we want to identify the most stable conformation for each of the molecules, and remember that for the stability of cyclohexanes, one of the key interactions is going to be the 1,3-D axial interaction, which is going to destabilize the conformation. So in most of the cases, the position with most substituents in equatorial positions is going to be preferred. So now, in this case, for the cyclohexanes that we're going to have, I'm going to use the numeration starting as follows: 1, 2, 3, 4, 5, 6, going in the clockwise direction towards the left over here. And in our cyclohexane rings, I'm going to keep the same convention: 1, 2, 3, 4, 5, and 6. Remember that whenever we do the ring flip, in order to get the second chair conformation, we're going to shift the numeration by one number towards the right. So with this, we can begin with the first molecule over here. We are going to have on carbon 1 position looking up. This is going to be an actual CH3 position. And in the carbon 2, we're going to be looking down. So we're going to have the following compound as follows. On the other conformation, we're going to have on carbon 1 an equatorial looking up position. And on carbon 2, we're also going to have, in this case, an equatorial looking down position, which is normally written as such, CH3. Notice that on the composition on the left, we're going to have an hydrogen atom over here and another hydrogen atom over here that are going to generate the so-called 1,3-D axial interaction. Something very similar happens on carbon 4 and carbon 6 with the hydrogen atoms that are looking down with the other CH3. So in the first case, the most stable configuration would be the one here on the right. Now, for the next one, what we're going to have is the following. Let's erase everything and reuse the image over here. So now for the second one, we're going to have two substituents that are going to be looking up. On the first chair that I have over here, the CH3 is on an axial position, and now on carbon 2, we're going to be in an equatorial looking up position. Whenever we translate this into the other chair, we're going to have our CH3 over here, and we're going to have the CH3 now in an axial, sorry, in this case it should be in an axial looking up position, as follows, CH3. So we're going to have equatorial up and axial up. In this case, we're not going to be able to have a more stable configuration because both of them are going to have the same stability. In both, the 1,3-D axial interactions are going to be with hydrogen atoms, and in both cases, we're going to have only two. In this case, the ones coming from these guys over here, and in this case, coming from these guys over here. So, no, both configurations are going to be equivalent. Now, as for the next one, we're going to have on carbon 1 and at carbon 4 an OH that is going to be looking down and a terbutyl group that is going to be looking up. So on carbon 1, on our first configuration, the OH would be in an equatorial looking down position. And in carbon 4, we would be, in this case, in an equatorial looking up position. This would be our terbutyl group. Now, when we translate it to the second configuration, what we're going to have is that the equatorial looking down position on the OH becomes an axial looking down, and on carbon 4, this guy is going to become an axial looking up position. So the most stable configuration is going to be the one on the left, because we're going to have the least amount of 1,3D axial interactions. And finally, we're going to have a configuration where we're going to have on carbon 1, 2, and 4 different substituents. In this case, on carbon 1, we're going to have our CH3. For carbon 2, we're going to have two CH3 groups. One is going to be in an axial looking down, and the other one in an equatorial looking down position. And finally, at carbon 4, we're going to be in an equatorial looking up position. When we do the ring flip, now in the second configuration, this guy is going to become an equatorial looking up position. Over here, we're going to have a CH3 and a CH3 over here. And finally, at carbon 4, we're going to have an axial looking up position, a CH3 over here. So as you may notice, we're going to have over here a 1,3D axial interaction in between two CH3 groups. This is now not only in between hydrogens. For example, on the configuration on the left, we're going to have this type of interaction with hydrogen atoms. But of course, the interaction with an hydrogen and the interaction with a CH3 is going to be very different. The interaction with CH3 groups are going to be way stronger, so that is going to destabilize more our configurations. So the correct one, the one that is going to be more stable, is going to be the one on the left. And with that, it would be all. Thank you very much and have a good one.